And the recording is live. Okay. Before we jump into today's lecture material, remember that we have our next exam on Monday. That's this next Monday, 5 days from now. And it'll encompass a lot of the past few topics that we've been focused on. Now, for the last 2 weeks, we've had some slight technical issues, mostly on this past Monday, where I wasn't able to record the lecture and had to resort to the board. What I have done is I have independently re-recorded a lecture that covers all of chemical kinetics, and that has been posted to Canvas. Secondly, you can see on Canvas under lecture, start of module exam 3 content. Lecture 11 says there's a suggested YouTube video. Don't forget that day I forgot to hit record. So I had linked a suggested YouTube video for practice, but I was able to find some archival footage from another semester that goes over molarity, that goes over different questions, but to the same extent that we covered in this class. So that is all to say, we now do have a recorded lecture for molarity featuring stoichiometry. It goes over slightly different questions than what we did in class. So I do recommend it as a supplement. And for those who may have missed that topic, or maybe the onboard lecture, whatever wasn't that mesh well with you, you can refer to this one right here. I've also posted this in the Discord. You can see under the last thing, it says archive lecture molarity featuring stoichiometry. The other bit is, if you recall, last Wednesday, 7 days ago, was my teaching evaluation. That's when we did the statistics workshop in the lab. Only the first 45 minutes of lecture was true material because I didn't want to overwhelm you with too much math. In other words, last Wednesday's material led into this Monday's material. And because of the lack of recording for Monday, it was a little bit confusing and we had to switch to the board. I have recorded a single 50-minute lecture that covers both last Wednesday's and this past Monday's chemical kinetics lecture. I do recommend you watch this. Number one, just like the molarity, it goes over a separate set of questions. Number two, since I'm working totally on the tablet, it presents the material in a much more visually cohesive manner than having to work with on the board. This is to say that both lectures 11 and 12, these recordings are effectively new to you. So if these topics do present issues, I recommend rewatching these videos from scratch. Our last topic that we're going to cover today, gas laws, lecture 13, will be the last material covered for Monday's exam. So this Monday's exam covers 3 topics: molarity featuring stoichiometry, chemical kinetics, and today's topic on gas laws, 3 topics. I'll go into further detail as to what you can expect regarding the exam once we finish gas laws. I can tell you as of right now, the draft has been made. It is an entirely multiple choice exam. You do not need a Scantron. As always, you'll have the entirety of lecture and lab to complete the exam. And as of right now, it's 25 questions in total, 25 multiple choice questions for a total of 50 points. So this upcoming exam is worth 50 points. It's 25 multiple choice questions. The 25 multiple choice questions cover the last 3 topics: molarity, chemical kinetics, and gas laws. So with the new recordings, you should be able to hit the ground running in your reviews and your studies, especially as you work on some of those extra credit worksheets. So those are the big announcements / housekeeping I wanted to get out of the way before starting today's topic. Today, we are talking about gas laws, or the gas laws. Apologies in advance if I sniffle. The weather changes have led to me getting a slight cold. Today, we will talk about gases and gas laws. Now, gases represents obviously the other state of matter that we have not spent too much time with. In other words, throughout the course of this semester, we focused on solids, we've looked a little bit at liquids, now we're officially looking at gases. But to first understand how gases work, one of the first questions we have to ask ourselves is, how do we know gases are real? See, it's one thing when it's something like a bottle of Febreze spray, when you can clearly spray the Febreze and you see those particles get dispersed throughout the atmosphere. There are other types of gases that are somewhat colored. I think of, for example, mustard gas, which by the term has that's not yet. The term mustard that has that slightly yellow tint to the gases. Don't worry, we'll go and turn this on. This happens every class. Okay, maybe I just didn't press it. Okay, that one's turning on. Oh no. Don't tell me this. Oh, no, okay. So it was there, accidentally turned it off. So I just need to turn it on one more time. Patience, patience is the name of the game. Okay, so that one's on in the back. What about the others? Okay, great. Okay. That was a little terrifying. I was worried I'd have to do another separate recording. Okay, sorry about that. Okay, so it's easy when we're talking about something like Febreze, where when we spray a can of Febreze, you can clearly see the particles. When we talk about something like mustard gas, as the name suggests, it has that slight yellow tint. And you can even think of something like straight up fumes from your stove. You can typically smell the gas. But with the lack of these features being smell, sight, how do we know that gases are real? I mean, we've talked about how in the atmosphere there is nitrogen, oxygen, and carbon dioxide. How do we know they're real? To answer that, let's go back a few weeks. Let's think about how we know solids are real. To know that solids are real, we weigh them. This, of course, leads to the unit of measure, grams for solids. We can measure the amount of solid present by just simply weighing it. In the case of liquids, we can measure their volume by way of graduated cylinder, pipette, beaker, et cetera, and this takes on liters, the units. So when it comes to solids and liquids, we have very clear, measurable, quantifiable units that we're able to say that we have a certain amount of liquid, we have a certain amount of solid, and we can know for a fact that it's there. Gases, on the other hand, we can't easily weigh them. We can't quite catch gases and put them on a scale. Similarly, you can't measure their volume. You can't pour it into a container because what's going to happen to the gas? It's just going to escape. What we can do is we can measure their pressure. And the units of pressure is ATM, not yet, AKA atmospheres. Now, where does this concept of pressure come from? Well, let's think back to our first discussion of gases. We talked about how a gas, as a particle, the gas molecules are consistently moving around high speed. They're all over the place. They're nicely dispersed, a lot more so than liquids or solids. What we see here are that the gases, the gas particles, are very mobile. And as a result of this mobility, they frequently collide, not just with each other, but with the walls of the container. These particles will collide with one another. They'll also collide with the wall of the container itself. It is that collision that we're able to measure. In other words, the pressure of a gas is equal to the force it exhibits over the area of collision. By measuring pressure, we can, number one, verify that the gas is in fact real, and it allows us to provide, again, a quantifiable, measurable scale of a gas, just as we talk about solids, liquids, and gases. In other words, just as you would say there are 10 grams of solid, just as you would say there are 10 liters of a liquid, you could say that there are 10 atmospheres of a gas. Now, that term ATM, aka atmospheres, may be recognizable to some of you. This is the SI unit for pressure, in which it is traditionally measured via barometer. You notice any weather station would most likely use barometers to measure pressure. But there are other units of pressure that we know we may not be able to immediately recognize, but we do have some experience with. Now, we just talked about ATM, atmosphere, as being the SI unit. You may also see millimeters mercury, mmHg, if you've ever gotten your blood pressure taken. Again, the pressure. I think the typical range is like 120/70 or something like that, mmHg. You might also see torr. This is normally used in the context of engineering. Another common one that if you have a car you would recognize is PSI, pound per square inch. If you ever had to fill up your tires, you know that almost every vehicle has an ideal amount of air in the tire. That's related to the PSI, pound per square inch. And the other one that's most commonly seen is PA, as in Pascal. All of these units together, just as we saw with mass being grams, kilograms, milligrams, and liquids, fluid ounces, milliliters, we have various units for pressure. But the one we will most likely be using, or rather be consistently using, is ATM, aka atmosphere. But it does become useful to remember what our conversions are. In other words, since everything we're going to be using is terms of atmosphere, what does it look like when we convert these to millimeters mercury, torr, PSI, or PA? Well, I'm here today to tell you that 1 atmosphere is equal to 760 millimeters mercury. 1 atmosphere is also equal to 760 torr. That is not a typo. It's the exact same number, 760. 1 atmosphere is equal to 14.69 psi, and 1 atmosphere is equal to 101,000 pascals. These are the standard unit conversions that we might encounter or might have to perform throughout our calculations. Now, as it pertains to gases, there is a single equation that relates not only that measurable value that we have, pressure, but to a whole other litany of variables. This is what's known as the ideal gas law. The ideal gas law is defined as PV equal nRT. You'll most commonly hear scientists refer to it as PIV-NERT. PV equal nRT, when sounded out, sounds like PIV-NERT. Some of these variables we already know. P, of course, is pressure. Standardly will be in atmospheres. V is volume. That will be traditionally in liters, as we've seen so far. N is the number of moles, whose unit is mol. And R, that's our new one, is what's known as the universal gas constant. It is a new term that we are introducing. It is known as the universal gas constant that has an exact value of 0.0821 liters atmosphere all over mole Kelvin. Now, in this R value, the universal gas constant, we do see the units that we have come to expect. L for volume, atmosphere for pressure, mole for moles. The only one left that's a bit outstanding is K, as in Kelvin. The only variable we haven't talked about so far is T, which is temperature. And in the context of gases, temperature will always be in Kelvin. K as in Kelvin. Now, some of you may recognize that word Kelvin. We did talk about it very, very briefly at the very beginning of the semester when we talked about SI units. We're all pretty much accustomed to the general measures of temperature, Celsius or Fahrenheit. But Kelvin is used scientifically because it avoids any zeros. So the first question, of course, is how do we get Kelvin? Well, that's a pretty simple thing. To go from Celsius to Kelvin, you simply add the Celsius amount to 273.15. To go from Kelvin to Celsius, you simply subtract 273.15. The Kelvin scale represents one of the most unique unit conversions because you're not multiplying or dividing anything. You're quite simply adding or subtracting. Meaning, unlike 1,000 mils is equal to 1 liter, unlike 1,000 grams is 1 kilogram, to convert between Celsius and Kelvin, we simply add or subtract 273.15. We will most likely not be encountering Fahrenheit, just to keep it simple. We'll only be working with Celsius and Kelvin. I want to make it abundantly clear, you always have to convert to Kelvin. Whenever dealing with gases or any types of these equations that involve temperature, you have to convert to Kelvin. And the reason is just more that we know about the temperature 0 degrees Celsius. This is freezing point. This is a very commonly encountered temperature. If you've ever been to New York, temperatures get to this amount fairly regularly. If you were to put that 0 number anywhere in this equation, all of a sudden, anything times 0 is, of course, 0. So by nature of it being 0, the data is more or less meaningless. So we purposefully convert to Kelvin by adding 273.15, because in doing so, we remove any possibility of our equation being multiplied by 0 or being divided by 0. So we always have to work with Kelvin. Now, that ideal gas law that we talked about, that PIVNERT, is the fundamental equation about gases. And from the ideal gas law, we are able to devise different derivations of it. Derivations of PV equal nRT. Now, starting from the equation, PV equal nRT, if we purposefully divide both sides by the number of moles and the temperature, what we see is the following equation. PV divided by NT is equal to R. Of course, all I've really done is just modify the equation. Don't forget, though, that that R value is a constant. It's 0.0821 liters atmosphere all over mole Kelvin. It is a constant. The implication of this is if this constant is in fact a constant, if, for example, we measured a gas at 9:02 in the morning at an initial recording, we would be able to say that the pressure and volume that the gas exhibits divided by the number of moles and temperature is equal to the gas constant, where I stands for initial. By the same code of logic, if we were to measure again, but this time at a later time, let's just say 4:05 p.m. This is our final measurements. We can again say that PV divided by NT is equal to R, the gas constant, where F refers to final. These simple equations tell us one thing. If we were to summarize it, A is equal to B, C is equal to B, where B, our gas constant, is a constant. And just as we saw in stoichiometry, we can actually relate these two such that A is equal to C, which tells us that for any gas, the initial pressure, volume, number of moles, and temperature will be equal to the final pressure, volume, number of moles, and temperature. In this way, we have now devised a brand new equation, or rather a full expression, that allows us to relate the different pressures and volumes that a gas might exhibit at different temperatures. This is what's known as the complete gas law. Not the ideal, but the complete. You may also see some textbooks refer to it as the combined gas law. It's important to understand that each of these variables in some way, shape, and form are subject to change. If you were to leave a cup of water outside for the full day, assuming it gets to at least in the hundreds, it'll slowly evaporate such that by the end of the day, the amount of water has decreased. Same thing with something like a solid. Maybe not over the course of a day, but over the course of years, maybe decades, the mass of a solid will change. The same thing can be said for gases. We talked about pressure being those collisions. Since collisions are something we try to attain, it may change. Similarly, the volume of the gas might change. And finally, the ambient temperature of the surroundings might change. This is most notable over the course of a day, where in the early morning it's probably cooler, and in the afternoon it's probably warmer. The only one that we do not really expect to change is the N, number of moles. For the purposes of Chem 1A, we will not deal with mixed gases, aka some sort of hybrid gas type. We will not deal with mixed gases. And the big takeaway from this is more often than not, N will be a constant. Based on this, since we know N will be constant, they can be canceled out. The overall equation that we will see, the overall law, is P1 V1 all over T1 is equal to P2 V2 all over T2, where the 1 and 2 simply refers to that initial and final readings, the first reading and the second reading. Now, it's important to understand use of the gas laws, the combined versus the ideal gas law. So let's talk about the situation you'd use one or the other. Over here on the left, we have the combined gas law. Over here on the right, we have our ideal gas law, Pivner. The combined gas law is used when studying a gas at different time points. At different time points, aka there is a very clear initial reading and there is a very clear final reading. On the other hand, the ideal gas law is used when studying a gas at a moment. At a moment, aka instantaneous. We're not looking at what it was in the morning and the evening. We're just looking at just a specific time of day. When we talk about the ideal gas law, its utility is, of course, obvious. It allows us to investigate various features or variables about a gas at a very specific moment. But the combined law is, in its own way, very useful. You see, when we talk about the utility of the combined gas law, we see various mathematical expressions. You see, starting from the very simple P1 V1 all over T1 is equal to P2 V2 all over T2. Don't forget the ones and the twos simply refer to initial and final, aka first reading and second reading. And remember that for Chem 1A, we traditionally will assume N to be constant. So it's traditionally not included. We can actually manipulate this equation in various ways. For example, if we're trying to find P1 alone, what we would do is we would multiply the entire thing by T1 over V1. Where does that come from? Why do we do that? Because when we multiply this side by T1 over V1, the T1 and the V1 cancel out. And remember, whatever we do to the left-hand side, we have to do to the right-hand side, such that we are able to say P1 is equal to P2, V1 is equal to P2 times V2 all over T2. All of that multiplied by T1 over V1. You can, of course, abbreviate this further, put it all in one single expression, P2 V2 T1 all over T2 V1. It's the same thing. We just put it all together and simplified. And hopefully the utility has become clear. If we know various values, measurements at different time points, P2, V2, T2, T1, V1, we're able to very easily and simply calculate another variable, in this case, P1. We can apply that same logic to instead try to get, for example, V1. What if we want to leave V1 alone? Okay, have V1 by itself. What would we do here? To get V1 by itself, we would multiply the entire thing by T1 over P1. Why? Because in doing so, we cancel T1 and we cancel P1, leaving V1 alone, such that the final answer is P2, V2, T1 over T2, P1. So the utility of the combined gas law should be very clear. From this very simple expression, from this very simple relationship relating initial and final, we're able to get a litany of new equations that allow us to simply plug and chug. And don't forget, the concept of the combined gas law did in fact come from the ideal gas law. The subsequent utility of such an equation is that it allows us to graph the various relationships. This is going to be 4 graphs in total. So 4 sections. The axes will change in no particular order. Up here, we have pressure, volume, then we have volume and temperature. Then we have pressure and temperature. Finally, we have volume and number of moles. 4 graphs. I'll give everyone just a second to draw the axes and all that. The beauty of the combined gas law is that we're able to make very broad predictions and statements about a gas. For example, when measuring pressure versus volume, only 2 variables, we are allowed to assume that the temperature is constant. In other words, when we're measuring pressure and volume and keeping temperature constant, we see the relationship between the two is simply P1V1 and P2V2. The graph looks like this. We can see that as pressure decreases, volume increases. So as pressure increases, volume decreases. Similarly, as pressure decreases, volume increases. We can apply that same set of logic to the other graphs, only focused on the variables mentioned. We have volume over temperature. How did I get here? Don't forget there is traditionally a pressure included, but by nature of this graph, only measuring volume and temperature, we're allowed to assume pressure is constant. The relationship between volume and temperature is a positive slope. The implication of this is that as volume increases, so does temperature. Similarly, as volume decreases, so does temperature. The two have a linear relationship to one another. Next, when talking about pressure and temperature, again, looking at the equation, P1 over T1 is equal to P2 over T2. Since the axes only really refer to pressure and temperature, we are allowed to assume the volume is constant, hence it's deleted. And here again, we see that the graph is a positive slope overall. Where just as the previous case, as pressure increases, so does temperature. As pressure decreases, so does temperature. We can also do the same thing for a graph comparing volume and number of moles. V1 over N1 is equal to V2 over N2. Remember where this came from. The original combined gas law is P1V1 over N1T1 equal P2V2 over N2T2. The graph only refers to volume and moles, so we're allowed to assume pressure and temperature are constant. Now, I know I already told you that for Chem 1A, we will not be dealing with mixed gases. So N will almost always be constant, but it's still important for you to see the relationship between volume and moles. Here, we again see a positive slope overall. As volume increases, so does the number of moles. As volume decreases, so do the number of moles. So from the very simple ideal gas law, Pivnert, we're able to derive the combined gas law. And from the combined gas law, we're able to make four broad conclusions, four broad statements that relate various variables: pressure, volume, temperature, pressure, temperature, volume, and number of moles. Now, these graphs, these ideas weren't just picked out of thin air. Specific people were behind them. You don't necessarily need to memorize their names, but it's good for you to know. Pressure and volume was identified by Boyle. Boyle is the one who really said, hey, I want to look specifically at pressure and volume. Similarly, Charles looked specifically at volume and temperature. Pressure and temperature was investigated by a duo, Gay-Lussac. And our volume and moles was investigated by a very familiar name, Avogadro. So not exactly contemporaries, not exactly rivals, but rather just scientific colleagues, kind of all within a few years of each other. They were simultaneously studying this. They all independently looked at two different variables. And their studies all together led us to what we know today as gases. Now, the content of gases is pretty much that. I'm going to start handing out today's workshop, and we're going to go through a couple questions together. Because the challenge isn't with the gases concept, it's with the math behind it all. And a spoiler alert, we will be using the roadmap today. Four copies. Two copies. Okay. This is a copy of today's workshop. We're going to take a couple questions from it and solve them together. We're going to do a couple variety of questions. Let me see if I can just get the document on my end. Let's get out our calculators because we will most likely be using it. Okay. Now that we've switched into doing some questions, we have officially ended all new content for module exam 3. So as of this moment, no new content will be introduced. We'll just have some time to do some practice questions, which will lead us into today's workshop, in which, of course, as always, you'll do some questions on your own and then have some assigned as extra credit. We're going to do a couple questions together. Let me just arbitrarily pick. I'm going to pick number 1 and number 3 so far. Let's work on them together. Let's read what the question says and try to understand what we're being asked to do. I'm going to need some space for number 1. So let me just take a picture of it so I can move it over. All right. Number 1 clearly states 22.5 liters of nitrogen is compressed from a pressure of 748 to 725 millimeters mercury. What we are being asked to find is the final volume. Now, the wording of this question gives away which equation we're going to use. Through the question, we're told that we have some volume of gas and we're told that it's compressed. We're also told that we had some pressure at the beginning and some pressure at the end. In case it's still not clear, the question does outright say calculate the final volume. In other words, the wording of this question tells us we are studying a gas at different time points. That is what tells us we will most likely be using P1V1 all over T1 is equal to P2V2 all over T2. That word final is used. We see some other phrases like compressed from. So we have a clear initial readings and a clear final readings. Let's take a look at what they are. From the wording of the question, we do have a couple values. We're told the volume is 22.5 liters. We're told that the pressure, the initial pressure, is 748 millimeters mercury. How do we know it's our initial pressure? Read the wording of the question. It's compressed from. It's compressed from a pressure of 748, so it starts at 748. The final pressure, we're told, is 725 millimeters mercury. And we're being asked to calculate the final volume, aka V2. That is, of course, what tells us that the volume we were given was the initial volume. Now, I have been using ones and twos to clearly delineate initial and final. It is fine with me if you use I for initial and F for final, whatever makes the most sense to you. We see here from the question, we have pressure, volume. There is no mention of temperature anywhere. The fact that temperature is not mentioned anywhere is our clear indicator that temperature is constant. It is not mentioned at all. There is no mention of it starting or ending. The fact that it's not mentioned tells us it's assumed to be constant. Based on that, we will be using the equation P1V1 is equal to P2V2. This is what Boyle did. He specifically varied pressure and volume. Now, identifying that Boyle did this doesn't actually help you with the question, but it's some context to provide as to how these kinds of things took place. Boyle was a scientist who was like, well, I know the combined gas law has pressure, volume, number of moles, and temperature. I only want to look at pressure and volume. That's how we know what equation we're going to use. Now, at this point, recognize that we have P1, we have V1, and we have P2. All that's left is to calculate V2. So at this point, it's just a matter of plug and chug. Now, you have two general approaches with this. You can rearrange first and then plug. So I'll just write that phrase out. Rearrange, then plug. Or you can plug, then rearrange. What exactly does that mean? How exactly do you know what to use? Simply put, it just depends on what you want to do. You see, we know here we're trying to find V2. So we need to get V2 alone. To get V2 alone, we will say P1V1 is equal to P2V2. We will then divide both sides by P2. In doing so, we cancel out P2 on the right. and we write this a little better, we get a very clear V2 is equal to P1 V1 all over P2. So we have rearranged first. Now we're going to plug in the values. Very good thing that we spend some time identifying the values over here. We're just going to plug them in. P1 is 748. V1 is 22.5. And P2 is 725. Now note that the units of pressure in this case are millimeters mercury. We do not have to convert them because this is just another unit of pressure. If we needed to, we could convert it to atmosphere, but we don't need to. We're going to put these values into our calculator. We have 748 multiplied by 22.5 all over 725 for a whopping total of 23.21. And which brave soul wants to tell us what the units of V2 are in this case? Liters. How do we know they're liters? Because the initial volume was told to us in liters. That's the first approach. We rearrange and then plug in. The other approach is to plug in first and then rearrange. Let's see what that looks like. P1 V1 is equal to P2 V2. We're going to plug in these values. P1 we know is 748. V1 is 22.5. This is equal to P2, which we know to be 725. And V2 is left. Now we're just going to put some of these values in our calculator on the left-hand side. 748 times 22.5. This is 16,830. That's equal to 725 times V2. To get V2 alone, we're then going to divide both sides by 725. We put this into our calculator. To no one's surprise, we get the exact same number as before. 23.21 liters is equal to V2. So as you can see, the specific approach you take, rearrange, then plug, plug, then rearrange, it still leads you to the same answer regardless of the approach you take. The choice just comes down to whichever you're more comfortable with from your math background. Either you're the type to want to get the proper equation first and then put it all in your calculator, or you'd like to do the calculator bit by bit. Both approaches will lead you to the exact same answer. Do we have any questions on number one? Notice that from molarity and kinetics and now gas laws, this next exam is a very calculation-heavy exam. So I do recommend while you practice and you're studying, learn your calculators. Learn where the buttons are, how to use it, what common mistakes we make. Because this is the kind of exam where you can understand all of the material. But if you input something in your calculator wrong, if you misread your calculator, you will go incorrect overall. Let's try another one. Let's try problem 3. All right. We've been through a question before. Let's try to speed things up. The question is asking us calculate the pressure required to compress 196 liters at 1 atmosphere to a final volume of 26 liters. Whole lot of context here to tell us that we're going to be using the combined gas law, P1V1 over T1 is equal to P2V2 over T2. Let's take a second to identify what values we have and what values we're being asked. We're told that V1 is 196 liters. We're told that V2 is 26 liters. How do we know that? Just pay attention to the wording. We're told that the final volume is 26. That means the initial volume must be 196. P1, since we know that this 196 is initial, we're told that that's the volume at 1 atmosphere. The wording of the question tells us that's P1, 1 atmosphere. That means we're trying to calculate P2. There is no mention of temperature, no mention of moles. That's what tells us temperature is a constant. To get P2 alone, we're going to divide both sides by V2. P2 is equal to P1 V1 all over V2. We've already taken a second to identify our values, so we plug it all in. 1 times 196 all over 26. 1 times 196 divided by 26 is equal to 7.54. What are the units? Atmosphere. How do we know that? Because that's what the pressure was given to us as, atmosphere. One of the most commonly encountered mistakes for this chapter is not just the calculator, but it's incorrect assignments. For example, V1 and V2. You see, even though the question said final volume is 26, some students think that's V1. And of course, that will mess up your math overall because your values are in the incorrect places. So being able to read these questions is as important as being able to solve these questions. Let's try another one. And let's do number 5, specifically because it involves temperature. This is number 5. Number 5 reads, a weather balloon is filled to 150 liters at 10 degrees. It cools to -8 degrees. We're being asked to find the final volume. Again, the wording of the question clearly tells us this will be a P1 V1 all over T1 approach. Taking a second to identify our variables, we know that V1 is 150. Based on the wording of the question, we're trying to find V2. We know that temperature 1 is 10 degrees Celsius and temperature 2 is -8 degrees Celsius. There is no mention of pressure anywhere here. So we can erase it from the equation. It's assumed to be constant. And we need to find V2 over here on the right. To get V2 alone, we will multiply both sides by T2. That cancels out the T2 on the right. What we're left with is V2 is equal to V1 over T1 multiplied by T2. And when we plug this in, we get 150 divided by T1 of 10 multiplied by T2 of -8. We put this into our calculator 150 divided by 10 times -8, and we get -120. That's what tells us our final volume is -120 liters. But as I write this, something about that statement should really piss you off. Volume cannot be negative. As a value, as a concept, it cannot be negative. So what did I miss in my calculations? You gotta change it to Kelvin. And hopefully this example shows us why we have to convert it. Sometimes we will be dealing with negative temperatures, and that leads to an answer that just doesn't make sense. So we have to convert the temperatures to Kelvin by adding 273.15. So the 10 degrees, 10 plus 273.15 is equal to 283.15. And for the Celsius, we're again going to add that -8 to 273.15. Putting this in our calculator, we get 265.15. By doing that very simple conversion, we now update our calculation 283.15, 265.15. We're now able to put this in our calculator. 150 divided by 283.15 multiplied by 265.15 for a whopping 140.5. This is a much more reasonable number that makes sense. So the big takeaway from number 5 is to always convert temperature to Kelvin. We did not need to do it for the pressure. We didn't need to do it for volume, but we have to do it for temperature. Because using our non-converted, such as in this case, the -8, we got a negative answer overall, which doesn't make any sense mathematically. Do we have any questions on number 5? Okay. The first page of today's workshop, page 1, numbers 1 to 10, really go over a lot of that combined gas law manipulation and usage. We haven't yet invoked our PivNerd. So let's do a couple questions from the second page. Let's start with number 11. All right. Immediately, we know something's different. How do we know that? Well, the question gives us an equation. The question reads, how many grams of chlorine is needed to produce 1.6 liters of nitrogen at 1.2 atmospheres and 23 degrees Celsius? The wording might sound really confusing, but look at what's happening. We're being asked information about one chemical after given information about another chemical. We will be using the roadmap. So we're going to connect Cl2 and N2. And I'll take a couple seconds just to draw up my roadmap, as will you. Mass, moles, volume. We know what's between these boxes, our bus passes. We have molar mass. We have molarity. And we know what connects them is our ratio. As of right now, all I have done is simply drew the roadmap. Based on the wording of the question, we can fill it in. Ultimately, we're being asked for grams of chlorine. So we know that's where a question mark is going to be. We're also told that the nitrogen is 1.6 liters, and we're also told the pressure and the volume. Now, I know what you might be thinking. Oh, Sabrith, if the 1.6 liters is right there, isn't that the volume of the gas? Technically, you would be right. But think about what bus pass you would be using to solve it with. This is molarity. This is moles over liter. This is very much exclusively a liquid thing. So we can't put the 1.6 in this box because this box is for liquids. So we're going to need another box that connects correctly the volume of a gas, 1.6, where the bus pass used is Pivnert. I want to be super clear here. Yes, technically speaking, this 1.6 liters is a measure of the volume. So yes, you might think it goes into the volume box. But on the roadmap, this volume portion is only for liquids. Why? Because in those cases, we were dealing with molarity. It's the amount of stuff dissolved in a solution, liquids. N2 is a gas. We know that through two ways. Don't forget N2 is a diatomic element. We know from module 1, all diatomics are gases. In case you forgot that, look at the equation. The state symbol for N2 is gas. In fact, everything here is a gas. So that's what tells us we are going to need a new addition to the roadmap. Using the volume of the gas, using Pivnert, the road ahead is clear. Volume to moles, mole ratio, moles to mass. We're going to erase all the unnecessary bits just to reduce congestion. And we're able to clearly see the path ahead. First things first, we're going to be using Pivnert. Remember, nothing in this question tells us we're looking at two different time points. There isn't an initial, there isn't a final. We are studying a gas, a system at a specific moment. How many grams are needed to produce at a specific pressure and temperature? Using Pivnert, we will then divide both sides by RT to get N is equal to PV over RT, number of moles. We know from the question, the pressure is 1.2 atmospheres. We know from the question, the volume is 1.6. The gas constant, a constant, is 0.0821. And the temperature, 23 degrees. Please remember to convert it to Kelvin. Take a second to look at the values I've written and make sure you understand where each of them came from. Pressure and volume came from the question. The gas constant is a constant. And the temperature given to us in Celsius needs to be converted to Kelvin. We're now going to put this into our calculator. 1.2 times 1.6 all over 0.0821 multiplied by 23 added to 273.15. Hopefully we're starting to see where that calculator can be our worst enemy if you're not inputting it correctly. This entire thing is equal to 0.079. With that, we've now determined the number of moles of nitrogen and re-entered our classical roadmap. Step 2 requires the ratio. Looks like we need to balance the equation and all that nice stuff. 1 nitrogen, 2 nitrogens, no big deal, put a 2 in front. 6 hydrogens, 1 hydrogen on the right, just put a 6. Nitrogen is balanced, hydrogen is balanced. 2 chlorines, 6 chlorines, easily put a 3 in front. We can see that the ratio between Cl and N2 is 3 to 1. 3 to 1 is a nice simple ratio. It just tells us we're multiplying by 3. So now we're going to multiply that 0.079 by 3. We get 0.237. To get to mass, we need the molar mass of the chlorine. If we just took a second and wrote it over here to the side, the molar mass of chlorine is equal to 35.5 times 2. Remember, the mass of chlorine is 35.5, and there are 2 of them in total, so we can just multiply by 2 for a total of 71 grams. So our last step is in invoking the equation. We always know mass is equal to number of moles times molar mass. 0.237 multiplied by 71. Put this in our calculator. And we see here we get 16.83 grams. And this right here is our final answer. Yes, Kath.
Question or in part of the question, and we would just leave TL.
So the case of PivNert is that you don't have initial final. So I have to give you all of those values in some way, shape, and form. Yeah, I would have to give you those values in some way, shape, or form. It's only with the combined gas law do we worry about ignoring because it's assumed to be constant. How we doing? This is gases featuring stoichiometry. I made you a promise when we covered it at the beginning. We're going to see stoichiometry a lot for the rest of the semester. In fact, past this next exam, we're going to keep using the roadmap. We're going to add even more to it, just like the gases. I'm going to pass out another handout right now. Four. believe there's 4 in here. Is it not 4? Okay, that's fine. That's my bad. All right. I've just passed everyone out a formula sheet. This is the exact formula sheet you will be getting on your exam on Monday. You will also get the periodic table. You can see it at the very top right corner, Chem 1A Module Exam 3, October 20th. I just printed just that page. This is the formula sheet you will be given. You will be given this formula sheet on the exam. So the equations on this sheet, you do not need to memorize, but you do need to know how to use, manipulate, and exploit. I'm giving you this formula sheet ahead of time so it can aid you in your studies to make it clear what you do need to know and what you don't need to know. One of the immediate things I want to point out is that middle table. It says reaction order, integrated rate laws. Remember, that's chemical kinetics. I told you you needed to memorize the graphs, but you will be getting the equations otherwise. Do we have any questions? Okay. We're going to end lecture for today. It's 1:11. Our workshop starts at 1:30, and I'll tell you what your assigned questions are in your extra credit. Let's take about, looks like a 19-minute break. If you have any questions, come talk to me now. If not, see you in about 20 minutes.